So with that, I'd like to bring up our next speaker, Hajar Mosanif, who's here to speak to us today as the third speaker in this sensing workshop. Hajar, take it away, please.
Yeah, thank you very much. So last time, actually, I gave a TEDx talk. I was haunted by a dream, a big dream to change this world in some way or the other. I've always been confident that technology and artificial intelligence have the power to make people live happier. I worked really hard and have succeeded in developing many cool innovations ranging from the smartphone, which recognizes emotional states and reacts to them, to support humans emotionally, to Shama, the first 100% Moroccan robot who has lately joined the United Nations Fund for Population to fight against all forms of discrimination against women and girls. Well, 5 years after my talk, the world has indeed changed, but people haven't gotten any happier. In Morocco, COVID-19 has generated more unemployment, more social disparities, and more poverty. COVID-19 has also changed much in me. It has taught me that making people happier can't be achieved through creating cool tech, but more about guaranteeing decent living and ensuring people's basic needs. Agriculture in Morocco employs almost half of the population. About 57% of women are engaged in agricultural activities ranging from weeding to harvesting, planting, irrigation, and pest control. They also contribute to more than 50% of the agricultural labor. Large numbers of these women aren't receiving any education at all, with children forced to quit schools to support their families. Well, the massive adoption of technology in the agricultural sector will not only allow agriculture businesses to be more profitable, sustainable, efficient, safer, and more environmentally friendly, but it will also ensure that farmers in rural areas get given and decent education instead of spending several hours per day doing highly repetitive and physically taxing labor robots can efficiently do. In Morocco, we have succeeded in automating many tasks related to agriculture labor. Thanks to computer vision, many machines are now capable of identifying and sorting different fruits and vegetables according to their type and degree of maturity, like the video I'm going to show in a couple of seconds of a big company in Morocco, which is capable of making 200 decisions in 1 second and sorting 6 tons of vegetables in 1 hour. And this machine is 100% Moroccan made. We're also currently working on the first 100% Moroccan agricultural and computer vision powered robot to be deployed in a grape field as a first step. The robot will basically perform 3 main tasks: weeding, harvesting, and soil analysis. For the weeding operation, the robot vision system will allow it to follow the crop lines and detect the presence and location of weeds in and between rows. The robotic arms can, for example, spray chemical herbicides in a targeted manner or determine the necessary force to pull out the detected weeds. For the harvesting operation, the robot will leverage the power of machine learning to locate the crop, determine its type, degree of maturity, and whether it is eligible for harvesting or not. The soil analysis operation makes it possible to know the fertility of the soil, the availability of nutrients, irrigation parameters, as well as any changes to be made during planting or pre-planting. Data analysis and interpretation are, of course, essential at this level for good making. A key technology that allows the robot to fulfill such complex tasks is artificial intelligence, and more specifically, deep learning. Artificial intelligence allows machine to imitate a form of human intelligence by making the machine sense, reason, act, and adapt to its environment. So the idea is to let algorithms parse the data, learn from the data, and then make a determination or prediction about something in the world. In the case of our agricultural robots, this data consists in both images and sensor measurements. So we'll stick for images for now. Let me show you in very simple way how the robot detects and locates disease crops and weeds in an image thanks to deep learning and more specifically image segmentation. Weed identification can be color-based, shape-based, texture-based, or location-based. To build a deep learning model for such tasks, we need to train it with data. That is, we need to feed the algorithm with images with type and location of defects or weeds, and let the model learn how to locate them after it has been trained. It's worth to mention that defects, whether it is disease or weeds, can be challenging to detect even by human inspectors and also very time-consuming. Improving automation, increasing efficiency, and maintaining high quality in production are more than welcome. Many aspects have to be taken care of, especially when dealing with image acquisition and pre-processing. The distribution of images used for training has to be close to the same distribution of images that will be taken by the robot in real scenario deployment under different light conditions that are mainly affected by environmental factors such as sunny and cloudy sky conditions. So attention should also be paid to the selection of color space. In order to guarantee the accuracy of identification algorithm, a suitable color space is a prerequisite. At present, the most commonly color space models are RGB, red, green, blue, HIS, hue, saturation, intensity, and YCR-CB, where Y is the luma component, and CB and CR are the blue difference and red difference chroma components. In the YCR-CB color space model, the luminance and chrominance are separated, which is more suitable for processing images that are sensitive to illumination changes, which is the case here. In the process of images acquisition, some factors such as insufficient light and uneven exposure can result in images with noise. There will also be many dummy white pixels such as plant shadows, which would affect the accuracy of defect identification. So removing the noise pixels is necessary. Well, depending on the application, some other image processing techniques can be used. They include like background removal, histogram equalization, where, for example, an image is modified to get the optimum usage of its color scale, sharpening, where blurriness is removed, glare removal, which aims at reducing the white bright parts of the pictures caused by overexposure. And it's worth to mention that we do not systematically apply all of these methods at once. Depending on the context, some of those methods might significantly distort images and harm prediction. Well, for the weed detection operation, its data set is a good starting point. It's the first large public multi-class image data set of weed species from the Australian rangelands, allowing for the development of robust classification methods to make robotic weed control viable. The weed species image data set consists of 17,509 labeled images of 8 nationally significant weed species native to 8 locations across northern Australia. Well, when we have a multi-labeled image segmentation problem, as it's The case here, we generally use a binary classification model to filter images with defects from those with no defects, and then we use as many segmentation models as the number of classes of defects we have in images. Well, I know that this might sound confusing, especially for those who are unfamiliar with machine learning, but let me put it in a very simple way. So let's first start with our binary classifier. A very common way to build a binary image classifier is to use what we call convolutional neural networks. Well, these are special types of machine learning models that are inspired by how we humans recognize images. So the contours and edges of an image affect our perception. Well, you might not have noticed, but our brain captures the patterns in images to classify an object. Convolutional neural networks, or CNN, are trained to classify images by detecting some patterns, just like as we humans do. For in the case of facial recognition problems, the patterns will be like ears, eyes, colors, and hairs, and so on. In this image, for example, the low-level features such as small bands, lines, etc., are extracted at the initial convolutional layers of the CNN network. And when we go from layer 1 to the middle layers of the network, middle-level characteristics like nose, eye, lips are learned. The last layers of the CNN extract and learn the characteristics of an entire human face. So in practice, very few people train an entire convolutional network from scratch with random initialization because it is relatively rare to have like a data set of sufficient size to satisfy those constraints. Instead, what we do, it is common to pre-train a ConvNet on very large data sets, such as ImageNet, which contains 1.2 million images with 1,000 categories, and then use ConvNet either as initialization or a fixed feature extractor for the task of interest. An option would be to just replace the last fully connected 1,000 neuron layer of the ImageNet trained architecture with a multiple neuron fully connected layer. And this process is what is referred to as transfer learning. So transfer learning is a machine learning method which applies the knowledge from related but different domains to target domains, and this solves the problem of having few or even not any labeled data in the target domains. Well, of course, many flavors of CNN, such as VGGNet, Inception, RISNet, or Exception, can be used for pre-training, and they are all available in many deep learning frameworks with pre-trained weights and with very few lines of code. Well, to overcome the highly variable nature of the target disease or with identification application, a series of augmentations have to be performed on both the training and validation image subsets to account for variations in rotation, scale, color, illumination, and perspective. Image augmentation can be performed using specialized computer vision libraries such as OpenCV. The baseline classification performance on the DeepWeeds dataset presented earlier using Inception V3 and RISNet 50 was 95.1% and 95.7% respectively. Well, deep learning models are very powerful, but they can also make mistakes, like in here, where the model which was asked to generate captions for input images had mistakenly described a parrot as sitting on a toilet in bathroom, which makes no sense. Now that we built the binary classifier to distinguish weeds and diseases in images, let's dive into image segmentation to be able to accurately locate anomalies. By anomaly, I mean weeds or disease. In computer vision, image segmentation is the process of partitioning a digital image into multiple segments. So the goal of segmentation is to simplify or change the representation of an image into something that is meaningful and easier to analyze. Image segmentation is typically used to locate objects and boundaries such as lines, curves, etc. in images. More precisely, image segmentation is the process of assigning a label to every pixel in an image, such that pixels with the same label share certain characteristics. This will make it easy for the computer to learn from patterns in these multiple segments. So, for example, each pixel belonging to diseased plant is colored red. So the output of image segmentation is not just a class label, like in image classification, or some bounding box parameters, like it's the case in object detection. The output, in fact, is a complete high-resolution image in which all the pixels are classified. If we use a regular convolutional network, we lose the where information and only retain the what information, which is not what we want. In case of segmentation, we need both what as well as where information. So our agricultural robot needs to both detect diseased plants and weeds and locate them to spray herbicides in a targeted manner. Remember that large area bold type spraying of chemical herbicides is not only a waste of herbicides and labor, but also leads to environmental pollution and food quality degradation. So the challenge in image segmentation is both on the performance and on the speed at inference, allowing real-time analysis. And here, many end-to-end deep learning models or architectures such as fully connected convolutional network, FCN, ParseNet, and the UNet has been developed for this task. The UNet architecture has been widely extended in recent works to other widely used architectures such as Feature Pyramid Network, FPN, Pyramid Scene Parsing Network, PSPNet, SIGNet, Mask Region CNN, Deep Lab V3, and so on. They can be all implemented using very few lines of code. Note that in such architectures, the number of parameters is reduced, and the model can be trained with a small labeled data set using, of course, appropriate data augmentation techniques, which is very useful in our case. In Deep Lab V3, for example, a special type of convolution called Aether's convolution allows capturing multiple scales of objects. It consists of filters targeting sparse pixels with a fixed rate, allowing an increase in the resolution of the final output without increasing the number of weights, as you can see here. So the primary purpose of convolution in case of a ConvNet is to extract features from the input image and capture the local dependencies in the original image. SIGNet has simpler structure and its computing speed is faster. SIGNet demonstrated excellent results in pixel-level classification and is well-suited for processing the segmentation of small, irregular-shaped crops and weeds in fields. And the average accuracy rate of the SIGNet method exceeds 90% in comparison with the fully convolutional network and the UNet methods when applied on a paddy field. Well, we've seen in this through this talk how computer vision for image processing and artificial intelligence for the application of transfer learning can be leveraged to build systems that are able to perform agriculture-related tasks autonomously. These technologies can definitely help in meeting the increase in demand of agriculture products without draining the environmental resources the agriculture uses. Artificial intelligence can help unlock solutions to many of the worldwide issues, including hunger and food insecurity. So by actively contributing to the AI field, we will not only ensure a better future for us, but for all other generations to come. We need to direct our efforts towards building tech that really matters, tech that aims at solving real problems, tech that has direct impact on people's lives, and most in tech that ensures inclusion and preserves our humanity. And thank you very much.
Well, Hajar, that was excellent. And actually, as I was typing a question, you were answering it in real time, which is a good thing, I suppose.